Okay, so I had said that by Thursday or today, by midnight, actually, if you would like upload a just a rough sort of Beamer sketch of what your talk might actually look like, maybe with your buckets kind of put in there, just so I can see that you've at least got sort of the basics of how you would put a presentation into Beamer format. That would be fantastic. I did want to point you to one particular resource that is specific to this class, actually. And in fact, next week, I think next week, we're going to have someone from the library who is specifically devoted to math and science research. It's going to come in and just show you all of the different resources and things like that. But right now, I was going to kind of take you in here and show you this. If you just search for Cedarville University Library, I think research methods should come up. Okay, so hang on a second. Oh, research guides. Be in here. That's not the one I wanted. Research guides. I think they actually have one specifically, yeah, for science and mathematics. And if you go in here, there's actually a link to research methods. Do you see this? Yeah. And they have some cool things. This is Nathaniel Davis, who I'm hoping will be able to come talk to us next Thursday. And he's really kind of gotten things going in terms of making sure people are aware of various resources that we have. As you'll see, MathSciNet is kind of front and center, right? That's something that you've gotten well familiar with. There are also other things like SciFinder and Oxford Scholarship Online, JSTOR, which is where this paper came from that I just actually gave you. A lot of JSTOR articles are available for free. This one that I gave you is definitely free because it's almost 60 years old, okay? But JSTOR is another place where a lot of mathematics scholarship appears. He has some stuff on, just research tips. There's also a little section on avoiding plagiarism, which is sort of interesting. And then there's actually a LaTeX user's guide in here. If you want some help in terms of setting various things up, these are basically just somebody else made these videos, and they're just links to various YouTube tutorials on things. Here's one on a Beamer slide presentation, for instance. Okay, so those are just things that you could access if you were so inclined and you need some extra help. There's actually online resources that are free. I think this guide to LaTeX is actually, I think it might be free, but there are definitely lots of resources online that are free at this point. Back in the day, when I first started learning LaTeX and Beamer was a thing for the first time, there wasn't nearly the amount of resources. You almost had to be able to write code like a coder to be able to do Beamer, okay? It's sort of a disaster in some ways. I keep getting kicked off here, guys. I don't think I'm actually going to need this one, so I'm just going to leave it. Okay. Well, anyways, there's that. But what I wanted to do today, and I'm trying to sort of have you see as many research-like talks that actually make sense and aren't just like totally blowing you away, which sometimes I feel like that's what tends to happen in a lot of the capstone presentations, is you see kind of this culmination of material that has been built upon year upon year upon year. And in some sense, it's like, oh, wow, they've really learned a lot. In another sense, it's like, I don't understand a single thing that person just said other than what their name was. And that's just kind of the nature of the beast in mathematics a lot of times. There's incremental learning that takes place. And then when it comes time to actually present the material, sometimes you forget the process that you went through when you presented it. Sometimes it's just not possible to explain everything. It just isn't, okay? So what I was wanting to do today was expose you to another paper that I find to be incredibly just beautiful. It's called College Admissions and the Stability of Marriage, which seems kind of like a provocative title, right? but it's a really good paper. I actually always put everything that I'm doing here. Hang on a second. I think I have this open in here. So like if you go into Canvas and you go to files, for instance, in here I have this paper. It's the Gale Shapley Stable Marriages document here. Here's the paper that I went through earlier on divisibility tests that Dr. Fry and I wrote together, okay? And here's the presentation that I'm about to go through, the stable marriage talk. There's no way I'm going to get through the entire thing, but I'll at least get to a point where we can have some nice interaction around this topic for sure, okay? So let's talk about this, shall we? Okay, so there's this famous problem in basically an area of mathematics called combinatorics, okay, which is kind of thinking about the number of ways that you can put things together and thinking about properties that these things might have. Permutations are a classic object of study in combinatorics. Various kinds of matrices that you can count. Okay, one of you is looking at something called alternating sign matrices for your research project. That would be an example of a combinatorial object. And matchmaking for stability, the stable marriage problem, is a particular problem in the area of combinatorics proper. And in some sense also probability, but combinatorics really, okay? And here are the two guys that first started talking about this, David Gale and Lloyd Shapley. I don't think that they knew exactly how much mathematical research was going to be spawned from this little paper that they wrote back in 1962. It's a very short paper. It's only like 6 or 7 pages, okay? And literally, you'll read it through and you'll almost understand the whole thing the first time. If you just read it kind of slow enough, I don't think there'll ever be a moment when you're like, well, that doesn't make any sense at all. I mean, you might have to sit there and kind of think things through or whatever, but it's an incredible paper and it spawned a whole host of mathematical research, not the least of which is some of the work that my own advisor did. In fact, he did some more work on the stable marriage problem with one of my good friends in graduate school. So there's still research being done on the stable marriage problem even today, okay? And what is the stable marriage problem? Let's talk about this. So here's the thrust of what's happening. So Gale and Shapley talked about the problem, at least in its initial framing, was students being matched to colleges, okay, according to preferences of each, okay? So the colleges, and by the way, the colleges each had a quota that they had to meet, okay? And they call this number of students that they wanted to admit Q. So that was their quota of students. And each college could potentially have a different quota of students that they were willing to admit. One problem that colleges tend to have is they don't ever know whether a student is actually going to come or not. So they'll like admit a student saying, congratulations. And then the student says no. And the reason that student says no is because why? Well, there was a school that was higher on their list that they also got admitted to, and as such, they decided to go to that other school. So they were like, is there some better like systematic approach by which students in colleges could interact with one another so that that problem gets alleviated to some extent, yes? And maybe even eliminated entirely. And they actually came up with a way to do it. Now, it hasn't necessarily been implemented in colleges, but it's been implemented in a lot of other areas. Like for instance, the national, what is it called? The National Residency Matching Program, where doctoral, people who are getting an MD, degree, they have to do a residency. And the residents, what they do to decide what hospital they go to is they actually use the Gale Shapley algorithm to match candidates to actual hospitals. It's always done, okay? But we have to understand what this what we're even talking about here. So what is instability? Okay, well, instability occurs if there are two students, alpha and beta. That's actually an alpha right there, believe it or not. Okay, two students, alpha and beta, who are matched to colleges A and B, okay, respectively. So like alpha is matched to A, beta is matched to B, but beta, the student beta would rather be with college A, okay? And college A actually prefers beta as well. And so they're like, what the heck are we doing? Why did we admit alpha? You know what I'm saying? I mean, that student would rather be here and we would rather have them than this student here that stinks. I don't know why we ended up with this one. So we'd rather be with this student down here. Does that make sense? That's an instance of instability where you have two matched pairs and one of the partners in a pair prefers the other partner to their assigned partner and has that feeling reciprocated. Do you see what I'm saying? And if that happens, you have something called instability, because they're going to tend to want to like divorce their matched partner and go with the ones that they would rather be with. Don't you see? Yeah. Okay. So a matching of students to colleges that is considered unstable if there is any instance anywhere whatsoever of instability, right? That is two pairs that where one of the partners prefers the other partner and has that feeling reciprocated, okay? And otherwise it's called stable. Now, the big question that was on Gale and Shapley's mind was whether it's always possible to actually find a so-called stable matching. Is it possible to find a stable matching? And amazingly, the answer is yes, okay? It is always possible to find a stable matching, okay? And we'll see this in action here pretty soon here, okay? Okay, it's always achievable. They showed, the way they showed this is by actually describing an algorithm called the Gale Shapley algorithm, or GS algorithm for short, that found a specific stable matching. Okay, it actually found a stable matching. Okay, and what they did to like first deal with the analysis and make it easier to understand is they actually just initially imagined that there were exactly in students and in colleges. So the same number of students in colleges. And by the way, these assumptions can be dispensed with later on, but it's just easier to describe what's happening. If you have the same number of colleges and students, and the quota of each college is exactly one, that means they're only going to admit one student, which is sort of weird, but you're only going to admit one student, okay? And by the way, if you look at it this way, it's sort of like marriages, don't you see? Yes, you have one side over here and you have another side over here. It's like the students are basically like the men and the colleges are basically like the women, or vice versa. And you're basically trying to find a way to match up men and women in such a way that a stability is achieved. Stability is achieved. And what does stability mean in this context? Well, it means that there's no pair of husband-wife combos, okay? So there's a husband-wife here and a husband-wife here, such that the husband prefers the wife of that other partnered pair and has that feeling reciprocated. If that ever happened, woo, that's bad, right? That's an instance of instability. So a stable assignment of marriages is one that avoids all possible instances of that, okay? Okay, this is clearly more interesting to think about. It sounds like the stakes are much higher when you're talking about marriages, right? An unstable matching in this context means that there is some man alpha and some woman A that prefer each other to their assigned match. Yes? Okay, so here's an example right here. So this is kind of like a ranking matrix. We put the men, alpha, beta, and gamma down the left-hand side of this ranking matrix. And we put the women across the columns, capital A, capital B, capital C on here. Now, the first number in each of these entries right here is always the ranking of, they're the men's ranking of the women. Do you see? So if I go across the first row, for instance, A is ranked number 1, don't you see? Yeah. B is ranked number 2 and C is ranked number 3 according to alpha, yes? If you go across the second row, beta ranks A as third best, yeah? B as first best and C as second best. You see what I mean? And so forth. So, well, gamma ranks A second, ranks B third, and ranks C first. Yeah, it's interesting. Okay. And then the women, the second number in those little entries, the second number corresponds to the women's rankings of the men. So A ranks alpha third, beta first, and gamma second. Do you see what I'm saying here? And you go down that way. Okay. So we'll come back to that example later on. But the goal here is to find a way to match men to women so that we have no instance of instability whatsoever. Okay, no instance of instability is permissible to us. Okay, any questions on that? I'm going to try to join one more time because I am going to want to write at some point, but any questions on that so far? Does that make sense? Hopefully. Okay. So here's a couple of thought experiments for us to kind of to go through together. What if there is a man, a woman? Here we go. Yes. What if there is a man and a woman that prefer each other best? Okay. What must be true in any matching that hopes to achieve stability? So think about it. There is a man and a woman somewhere. So there's a man on one side and a woman on the other side that each is the number one choice of the other. What would have to be true in any stable matching with if that were true? They'd have to be married. They would have to get married. Do you see why? Because, like, for instance, if the man and the woman who rank each other first, if that man were married to someone else, he's clearly going to prefer that other woman that's number one to his assigned partner, and have that feeling reciprocated, for crying out loud, yes? Because he's first on her list as well, yes? So whoever she was married to, she would prefer him as well, because he was number one on her list. Therefore, if you ever have an instance where you have a man and a woman who are number one on each other's list, then they would have to be married to each other, yeah? Okay. What if, okay, second thought experiment. What if the preference list for the men and women are all the same? So like everybody agrees about who the most awesome man is, okay? Okay, all the women agree this is the most awesome man. All the women agree that is the second most awesome man, yeah? All the women agree that guy's the third best, yeah? And so on and so forth. And all the men agree that's the number one woman right there. And they all agree that's the second best woman, that's the third best, etc. Okay, so what would happen if everybody's preference list was the same? You understand, everybody's making their own preference list. Every man makes a preference list, rank ordering the women. Every woman makes a preference list, rank ordering the men. What would have to happen in this case if everybody's list agreed? All the women agreed and all the men agreed.
Well, the first of each would have to be paired with each other. And then out of the remaining unmarried people, the second would have to be paired.
Yeah, that's exactly right. So it's kind of an extension. It's a corollary basically of the first problem, yes? Because everybody would agree about who the first best was, yes? And therefore, in particular, the ones that everybody agrees on as the first best, man and woman, those two would clearly rate each other as first best, yes? And therefore, by number one, they would have to be paired with each other, yes? Okay. And then once they're out of the picture, you can basically eliminate them, okay? And then we would have to go down and the second, what do you think, what would have to happen with the second ranked on everybody's list? They would have to be paired together for the same reason, yes? If we're going to have a stable marriage, the number ones would have to be paired together, they're out. Then you would have to do the same thing with the number twos and so on and so forth, yes? So if all the women agreed on the rank ordering for the men and all the men agreed on the rank ordering for the women, the number ones would go together, the number twos would go together, and the number threes, et cetera, et cetera. Yeah, yes?
What happens if, like, had just the women ranked all the men the same, but the men ranked the women.
Well, that would be a little bit different. Yeah, that would be, then it would be a little bit more complicated. Yeah. So if all the women had the same preference list, you'll see later on, you'll see later on when we actually try to figure out how to find one of these things, like a stable marriage, you'll see what will happen when the actual matchings are made. This thing is like going crazy on me here. I think I'm just gonna leave. I'm gonna leave this thing forever. Okay, and we'll just have to deal with it. But yeah, we'll see in a minute once we get to the algorithm how that situation might be dealt with, but it's not quite as simple as what we've done here for sure. Any other questions? It's kind of an interesting little thought experiment. Okay, so here is the so-called proposal algorithm, okay? And what's amazing is the algorithm that Gale and Shapley came up with mimics basically the cultural paradigm that we actually employ, okay? Okay, so here's how it works. Sometimes it's called the deferred acceptance or the proposal algorithm. Now, here's the thing. Basically, the way that our proposal scheme works in practical real life, it really is kind of a deferred acceptance thing. You know what I'm saying? Like, I don't like propose to my potential wife, and the minute she says yes, boom, we're married like that. Do you know what I'm saying? There's like a period of time where there's kind of like a waiting period, right? And sometimes engagements get broken during that waiting period. Yes. Now, there have been cultures where it's been a little bit more stringent than that. Like if you read the New Testament story of Mary and Joseph, when Joseph proposed marriage to Mary, it was essentially a done deal. There was still a ceremony to be had, right? But actually breaking the engagement was considered a divorce in that particular culture, okay? But it probably wasn't as serious as perhaps an actual divorce that would have happened after the official marriage ceremony. But watch how this is going to work. It's going to be just like our modern rendition of proposals. So here's what happens. The men who all have their preference list and the women who all have their preference lists are kind of sitting there. And the men, all of them simultaneously propose to their best choice. Okay? The men all simultaneously propose to their top person on their preference list. Now, that means that some women might receive multiple proposals, don't you see? Yeah? So in round one, each man proposes to his top woman. Each woman evaluates her proposals, if any. It's kind of sad because some women might not have her proposals. That makes sense. Okay, she evaluates all her proposals, and what's she going to do? Think about it. She's going to take the top one. She's going to look at her list and be like, well, I'm taking the top one so far, right? But I'm sort of non-committal. I'm going to kind of keep this guy on my string here, and I'm going to accept this proposal until I potentially get a better one later on. Yeah? See what I'm saying? So each woman evaluates her proposals, if any, and accepts the best, rejecting all the others. And these women are now engaged. Okay, so those women are engaged to those initial proposals. Okay, so all the men propose to their top choice in the first round. The women evaluate those and keep the proposal and are considered engaged to the ones that they keep, and they reject all the ones that are lower on their list. Yes, and that means there's going to be some men in the second round that have to propose again. Yes, and what are they going to do in the second round? Well, they're going to propose to their second choice on the list. Yes, some men are currently in an engagement and they don't propose. Don't you see? They're already engaged from the first round. But then these men that got rejected in the first round propose to their second choice in the second round. And the same thing happens. Women evaluate this thing. And by the way, what could happen when that occurs is there might be some guys that propose to ladies that are currently engaged. Don't you see? But what could that woman do? Suppose she receives a proposal of marriage, but but she's currently engaged. Well, she can look at where that guy lands on her evaluation list. And if it's higher than her current proposal, what does she do? She breaks it. And she goes with that one. And now that poor guy who was engaged before now has to go back to the drawing board, don't you see? And so he's going to re-enter the game in round 3 and actually have to propose to his second choice. Does that make sense? And on this thing goes all the way down. Okay, again, in round 2, each rejected man now proposes simultaneously to his second choice, and his first choice didn't work out. Each woman evaluates her proposals, even if currently engaged, and accepts the best, breaking an engagement if necessary. Okay? Rounds continue so long as there are still rejected men left to propose, or equivalently, until each woman has received a proposal. Okay? Once every woman has received a proposal, I'm telling you, we're done. Okay, once every woman receives so for instance, just think about round 1. Suppose every woman receives a proposal in round 1. Remember, there's the same number of men as women. If every woman receives a proposal in round 1, boom, we're done. And actually, each man is going to be paired with his best woman. Don't you see? Yeah, his top woman. Okay. Rounds continue so long as there are still rejected men left to propose, or equivalently until women have received a proposal. Once each woman is engaged, we have a mass wedding. Okay? We have a mass wedding. Now, you should in your mind be thinking, how on earth do we know that we actually have a stable matching, or all of these marriages are stable? Does that make sense? Okay. So, okay, just a couple of things for you to go work on in Chuck's later on if you want. Okay, so you might be saying to yourself, remember there was in men and in women, right? You might be saying to yourself, yeah, how do we know that it actually terminates eventually? Well, I'm telling you, if you just think about it carefully, if you think about what's happening carefully, it does terminate in n-1 times n-1 plus 1 rounds. Okay, just think about it. I'm not going to tell you why right now, but it's a fun little exercise to kind of figure that out. Okay. What about like the mean number of rounds? How many rounds are there going to be on average? Okay. And that means if I think of my preference list as basically being random or something like that, like each person's preference list is random, what would be the average number of rounds? Okay. That's an interesting question. Why does this thing deliver a stable matching? We'll talk about that in just a minute here. Here's another thing that's interesting. Clearly, men and women can exchange roles, and the women could, in theory, propose instead. Yes, we could do it that way, of course. Turns out that the Gale Shapley algorithm is so-called proposer optimal. Okay, in the following sense, the proposing group simultaneously do as good as they could possibly do in any stable matching. Okay, so the ones that are proposing in this Gale Shapley algorithm are going to end up with the best possible choice on their preference list that they could possibly have in any stable matching. Okay, in any stable matching at all. Now, here's the thing that's kind of annoying. It's proposer optimal. So the men are as good off as they could possibly be. Okay, if the men are the one that are doing the proposing. Now, even though it feels like the women have all the power, because they're the ones that are like rejecting certain proposals, yes? It turns out that the ones that are being proposed to, namely the proposees, this is going to be the worst possible situation for them, okay? They're going to end up with the lousiest possible husband on their preference list. So in the Gale Shapley algorithm, the proposers do as best as they possibly can simultaneously in the stable matching that occurs. And the women do as bad as they possibly can, or the proposees do as bad as they possibly can in any stable matching, okay? Now, sometimes there will only be one stable matching, in which case it doesn't really matter, okay? But anyways, so what I wanted to do next is actually try to think about this third question. Why does this thing deliver a stable matching? And because I don't have access to my iPad right now, what I was going to do was actually, let's see here. No, I'm going to go here. I'm going to go to here it is right here, stable matching, yeah. So if you go into the paper that I just handed out to you and you turn to, let's see, where is this page? Yeah, there always exists a stable set of marriages. So they go through right here. Okay, and right here, they say that the marriage is stable. Okay, why? Why is the marriage stable? Why are the marriages stable? The set of marriages stable. We assert that this set of marriages is stable. This is on page 13, which is basically, I think, the 7th page or something like that. We assert that the set of marriages is stable. Namely, suppose that John and Mary are not married to each other, but John prefers Mary to his own wife. Okay? John prefers Mary to his own wife. You understand what I'm saying here? Okay. Then John must have proposed to Mary at some stage prior, don't you see? If John preferred Mary, he would have proposed to her before, don't you see? Because you proceed through your list systematically as the proposer. So he would have proposed to Mary earlier, and what must Mary have done at some point? Rejected him in favor of someone else, yes, that she finds more appealing. Yeah? Do you see? Well, that's a little bit, yeah, it's a little bit tricky, but yeah, well, proposer pessimal, proposee pessimal. Yeah, that's hard to see actually. But yeah, it is true that it ends up being as bad as it possibly can for the women. But it does feel like the women have a lot of power, right? But what's going on here is the men are basically at each stage, what's happening is the men are only going down their list as far as they need to. Does that make sense? Like they start at 1 and then they're like, oh, that didn't work out in order to preserve stability. So then I go down to 2. So the men are only proceeding as deep into their list as is necessary to get stability. Does that make sense? And even though it feels like the women have all this power, they're really kind of beholden to what the preference lists of the men were. Does that make sense? They still use their list to decide which proposals to keep and which ones to reject, but they're still kind of beholden to that, yeah? Okay, so anyways, John must have proposed to Mary at some stage and subsequently been rejected in favor of someone that Mary liked better, yeah? It is now clear that Mary must prefer her husband to John. Does that make sense? Mary would have to prefer her husband because she rejected John's proposal at some point. So she would prefer her husband to John, and therefore no instance of instability could happen between John and Mary. Yeah? So that's kind of interesting, right? Yeah.
So they don't have to necessarily be each other's number one. It's just
No.
that it's not reciprocated.
Yeah.
No,
No, they don't have to be their number one. That's right. Yeah. Yeah. They don't, right. No, nope. They don't have to be their number one. So stability simply means whoever I'm married to, I don't like somebody else better and that likes me better than they like their assigned partner. Does that make sense? That's what causes instability. Do you see? Okay. All right. Any other questions? So does it make sense why this would have to give a stable assignment of marriages? Okay, this proposal algorithm. Okay. So like I would encourage you to think about, I know I said it's kind of tricky, but it isn't that hard to figure out just in the way I was just describing kind of the men systematically going down through their list, why the proposers would be as good off as they possibly can in any stable matching. Yeah. So here's one example. Look at this. There's only one stable set of marriages indicated by these circled entries in this particular ranking matrix. Notice that in this one, so by the way, you could go through this and actually do the proposal algorithm if you wanted to. Like for instance, the men are alpha, beta, gamma, and delta, yes? Who would alpha, beta, gamma, and delta propose to in the first round? Who would alpha and beta propose to? A. Alpha and beta would both propose to A. Gamma would propose to B, and delta would propose to D. Don't you see? And since alpha and beta both propose to A, A would say, okay, I have to make a decision here. So who would A decide to hold the engagement of? Alpha. Okay. So in other words, alpha, gamma, and delta all would have kind of a held proposal after the first round. Does that make sense? And beta would be left out in the cold. So then what would beta do next? They would go to their second choice, which is D. Don't you see? Yeah. And they would say, okay, I'm proposing to D. D would currently be holding the proposal of delta. Don't you see? Yeah. But D would say, I rank beta second and I ranked delta fourth. They were my worst choice. Don't you see? Yes. Therefore, what's D going to do? Yeah, but D would break the engagement with delta and hold the proposal of beta. Don't you see? Yeah. Okay, which means alpha, beta, and gamma are currently, they currently hold proposals. Don't you see? Yeah. And delta is out in the cold again. Okay, so what is delta going to do now? They would propose to B, right? Because they had their first thing accepted, don't you see? Yes. Now they go to their second choice, which is B. Okay. And they say, okay, I'm going to propose to B. Now B, who was B currently holding an engagement to? Wasn't that gamma or something? Yes. B was holding the proposal of gamma. Okay. But B feels like gamma stinks. That's their worst choice. And therefore, they're going to switch to delta. Don't you see? Yeah. So they switch to delta and they kick gamma to the curb. Yes. So now alpha, beta, and delta all are holding proposals. Yes. And gamma's out in the cold. So what's gamma going to have to do? Gamma is going to propose to A. Do you see what's happening here? Gamma proposes to A. And who was A proposed to? Alpha, yes? A was engaged to alpha, but they're third on A's list. Gamma is second. Therefore, what's A going to do? It's going to break it off with alpha and go with gamma. Yes? So you end up right here. And that means alpha now has to proceed down their list to number 2. Yes? Where's their number 2? B. B, okay? So alpha is going to propose to B, but B is currently, remember, look, there was actually a circle around there. B is currently engaged to delta, who is second on their list. Yes, but alpha is third on B's list. So what's B going to do with alpha's proposal? It's going to reject it, and so alpha is going to have to go to C. Yes, and it goes to C and it proposes. And who was C? I don't even remember. Who was C? Did C even, I don't even think C had received a proposal yet, had they? I don't think C had received a proposal. These three right here, we had already kind of arrived at, yes? Alpha's going to propose to C, and C's going to be like, yep, and grab onto that like crazy. They hadn't been proposed to until that moment, yes? And at that moment, you know that you have your stable matching, yes? Which means alpha goes with C, beta goes with D, gamma goes with A, and delta goes with B. Yeah? So that's sort of interesting. Any questions on that? Yeah.
Wait, so didn't you say it would be the best for the men?
It would be the best for the men, yes.
But in this case, the men, all the men's ranking are 2, 2, 3, and 2, but the women's ranking are all at 2.
Right, but what I'm saying is that there could be other stable matchings in which the women actually do better. Okay, it doesn't matter, it's not about comparing rankings with men and women. It's like for alpha, what's the best possible ranking he could achieve in any stable matching? And the answer is 3. Does that make sense? For the women, like C, for instance, what's the worst she could do in any stable matching? Well, it turns out it's 2, according to this. Yeah. Okay. That's the worst she could do. There might be some where C could actually get her first choice, for instance. There might be other stable matchings where that happens. Okay. Does this make sense? Please. So any other questions on this? Well, how can we modify the Gale Shapley algorithm with quotas for colleges that are larger than one? Well, it's pretty easy. All you do is you imagine students. Now remember, whoever is doing the proposing is always going to do as good as they possibly can in any stable matching, yes? So it makes sense to kind of give that power to the student and not the college, okay? So what would happen is a college would have a certain quota, okay, that they would want to meet. The students would all propose to their top college choices, yes? And every college would keep as many proposals as they have a quota to keep. Does that make sense? So like if they have 5 students that they're willing to admit, they might keep as many as 5 proposals, don't you see? And then they would say, they would keep the top 5 proposals that they receive, and they would reject the others. And all rejected students would have to proceed down to the second choice on their list. And they would propose, and any college that is currently holding a number of proposals equal to their quota, they might have to reject, yeah, some that are lower on their list and receive other proposals that are up higher on their list. Does that make sense? So basically it works exactly the same, except the colleges are constantly shuffling people in and out of their quota. We were basically doing that with men and women also. It's just the quota happened to be 1, don't you see? They were just swapping out 1 for 1 all the time, yes? So it works exactly the same, which is kind of disturbing because it sounds sort of like we've given an algorithm for stable polygamy in some sense as well, don't you see, right? You could have like well, I guess it'd be kind of flipped around. You would have the women on one side doing the proposing or something. If you had a man with several women or something like that, you would have the women on one side, and the men would have a quota of women that they were wanting to marry or something like that. That's just sort of bizarre, right? It's better to think about colleges and students as opposed to stable polygamy, which is what I said right here, right? There is a way to actually achieve this, but it's just kind of bizarre. What about stable roommates, i.e. same gender? Okay, this is where the question gets a little bit interesting, okay? Stable roommates is actually another question that a lot of research has been given to. And there's still a whole bunch of open questions about stable roommates. But let me just show you something. So, by the way, we showed that no matter what the preference lists are, no matter what, this is an amazing thing. No matter what the preference lists are for the men and the women, we can always find what? A stable matching. Always. We can always find a stable matching. Do you understand how remarkable that is? Think about it. If you have men on one side and women on the other, even if everybody in the world made a preference list of every man in the world, and every man in the world made a preference list of every woman in the world, this algorithm would get us a way to pair off men and women in such a way that stability would be achieved, at least on the level of those preference lists. Of course, whatever, but at least we would be able to achieve it at some mathematical level, yes? But now I'm saying, what about stable roommates where anybody could basically be matched with anybody else? What about that? Well, think about this. Here's a classic stable roommates problem. Suppose there are 4 girls, A, B, C, and D, that need to room together in pairs, okay? All right? And let's assume this. Suppose that look, I'm not even going to tell you the entire ranking list, okay? Suppose that A thinks B is the best, B thinks C is the best, and C thinks A is the best. And everybody thinks D is terrible, okay? Everybody thinks D is terrible. What will happen? What will happen no matter what you do? So think about it. What if A goes with B? Then what would we have to do with C and D? Right, if A and B are together, C and D would have to room with each other. But C, okay, so C would prefer, everybody hates D. You know what I'm saying here? C would prefer A. Okay, hang on a second. C would prefer B, right? C would prefer B to D for sure, yes? And would B prefer to be with C than A? Yes. Right, B ranks C best. So C would prefer B and B would prefer C. Therefore, we would have an instance of instability. Don't you see? Yeah. Now I'm telling you, you could do the exact same thing with any other pairs. Anybody who is paired with D is going to cause instability. Don't you see here? Yeah. So do you see that something breaks down when you go to the stable roommates problem? Yes. That's sort of interesting. And by the way, it doesn't just happen with one big group. It also happens if you do anything other than two groups. If you go to three, something gets messed up. Or four, like for instance, a stable triplicate or something, yes? It turns out it doesn't work. It turns out you can always find instances of instability or stable quadruplicates or something like that, where this group of four ranks all of the other three groups, each person in each one of those, they give a preference list for it. It turns out that the only place that stability is guaranteed to actually exist, whether we find it or not is another question, is when you have one side over here and one side over there. I think that's pretty interesting, yeah? Especially given some of the cultural issues that we have right now, correct? Stable roommates problem, there is no guarantee of stability. In fact, there is a conjecture that's still like an open problem that almost no instances of preference lists actually contain a stable matching in the stable roommates problem. Almost none of them, okay? And actually, it turns out that if you have two sides, like you have the men and the women like this, you might say to yourself, yeah, but we found a stable matching, but are there a lot of them? Are there several stable matchings? And it turns out the answer is yes, on average. It turns out on average, if you have n men and n women, there's going to be like n log n times logarithm of n divided by e stable matchings. Okay, I mean, that might sound totally bizarre, like n log, where does the e come from? Actually, my advisor proved that, okay? That was one of the things he proved about stable matchings. If the preference lists are random, turns out that the expected number of stable matchings is n log n divided by e. And n log n, of course, goes to infinity as n goes to infinity. So that means on average, there are lots and lots and lots of stable matchings in a given collection of preference lists. And in the stable roommates problem, what is being said is that there's probably none. There are probably no stable matchings in that situation. I find that to be incredibly fascinating, okay? I think that's a nice conclusion to things, but I'll say this. This is at the end of the paper. Gale and Shapley say, the reader who has followed us thus far has doubtless noticed a certain trend in our discussion. In making the special assumptions needed in order to analyze our problem, mathematically, we necessarily moved further away from the original college admission question, and eventually in discussing the marriage problem, we abandoned reality altogether and entered the world of mathematical make-believe. The practical-minded reader may rightfully ask whether any contribution has been made toward an actual solution of the original problem. Even a rough answer to this question could require going into matters which are non-mathematical, and such discussion would be out of place in a journal of mathematics. It is our opinion, however, that some of the ideas introduced here might usefully be applied to certain phases of the admissions problem. And it turns out that they couldn't have been more right. At the time in 1962, when this paper was published, it was just seen as, man, that's really interesting. But it turns out that there's been a massive number of applications, even in the field of economics. Later on, Lloyd Shapley, who kind of started us thinking in this direction. Gale wasn't involved in this, but Alvin Roth got into the project later on and saw ways that this could be applied in economics, the stable matching situation. And they were awarded the Nobel Prize in 2012. By the way, this is 50 years after the original paper appeared, which just shows kind of like the timeline. Like they clearly saw this as just a mathematical musing, yes? And sometimes it can take a number of decades before you realize, or even centuries before you realize, oh man, this actually is pretty useful. Okay, so Shapley had laid the foundation in the abstract realm, and then starting with his joint work with David Gale in the 50s and 60s, and Roth realized starting in the 80s that Shapley's continued work could be adapted and applied in a broad range of practical scenarios, including doctors to hospitals, that is residencies through the National Residency Matching Program, students to schools in school choice. It hasn't necessarily been applied at the college level yet, but it has in other school situations. And even human organs for transplant recipients. The Gale Shapley algorithm has actually been used. They were definitely right to think that there could be some practical utility of what they did. Here's a little picture of residencies to hospitals. So the first choice for the doctor is the white arrow, and then the dotted white out arrow is their second choice, yes? Okay, so this doctor and this doctor here. So the doctors propose to their residencies. So what would happen in the first round? Think about it. Think about it here. What would happen in the first round if these doctors proposed to their residencies of choice? Wouldn't they all propose to that hospital up there? Maybe that's Johns Hopkins or something, yes? So they all three say, I want you. And who's hospital A going to keep the proposal of? One, and he's going to reject the other two. So then 2 and 3 are then going to propose to their second choices, which are B and C respectively, yes? And therefore, what's going to happen here? 1's going to end up at A, 2's going to end up at B, and 3's going to end up at C, yes? Okay, so this has actually been applied in residencies matching with hospitals in that particular paradigm. Okay, I thought that was a cool little paper. I would encourage you to actually read through it. It's a really interesting paper to read, and it's weirdly, it doesn't have like tons of math in it, but some of the underlying ideas are deeply mathematical for sure. All right, that's it.